So now I will, just because of time, I will go ahead to talk about the overview of quantum computer. I'm sorry, some of you might be very good already, but I still want to talk about this a little bit because it's useful for some audience. Quantum computer is important because it uses two phenomena, superposition and entanglement, in the computation. We have been using quantum mechanics in our classical computer. We know that, right? Because, for example, the transistor is developed, it has band gap, it's all based on quantum mechanics. But it does not use superposition and entanglement to do computation. There are two major types of quantum computing. One is the gate model, and other is the quantum annealing. Gates model is just like our classical circuits, right? We have a signal goes in, and then you have different gates. Eventually, you get the results that you want. Another that is also very promising is the quantum annealing. We basically map some of the difficult problem, for example, optimization problem, travelers, the salesman's traveling problem, right? Map it to some quantum system, and then we let it find the minimum energy. So the quantum system have different configuration, right? We hope that eventually it will find the minimum energy, and then that will correspond to the optimal solution. That is what D waves have been doing. And just one critical point is that in this type of annealing system, you are allowed to have tunneling. So it is easier to find out the minimum energy compared to the classical annealing algorithm. So in this talk, I mostly will talk about the gate base, because the gate base is more versatile. It's just like a general processing unit. But on the other hand, it is very susceptible to the noise. So that's why at this moment, it is not successful yet, right? We know it is important because it can help to solve some very difficult problem. So this can help us to design material, design the drug, right? Or even do quantum machine learning to speed up some of the quantum algorithm. Another useful thing is it can use for secure communication. I guess everyone already heard about this, right, before. So let's just quickly take a look what is quantum computing. In a classical computing, we have 0 and 1. We use it to represent the information. How do we represent it? You can use the coin, head and tail, happy and sad. I think we can do that also. And then our transistor open and short. In summary, I just want to say all the information are represented by the state. Now, that is very important concept, the state. Every physical system has a state. How about for quantum computing? It is the same. And particularly in each system, because of quantum mechanics, it has some basis state, which is more fundamental. So in that case, I also can represent the information by 0 and 1, except that here, I just have a different notation. It really doesn't matter. It's just a notation. We call it the Dirac bracket notation, right? So do not feel uncomfortable. What I did is just put it in a bracket. So similarly, I can represent with head and tail, happy and sad, open and short of a transistor, right? They are just basis, they are just a symbol I put it inside the bracket, and they all can represent the same information in the classical computing. No difference, except how I notate it, right? So what is so special about quantum computer? It is that it has some state that can be in a superposition of the basis state. For example, I have a state called psi, right? Again, I put it in a bracket, just a notation, right? You just accept it. It is a linear combination of two basis states, 0 and 1. And you have the coefficient in front of it. These are just numbers. So if that is the case, we even can understand it as like this. What is the state of a spinning coin on the table? Well, you don't know whether it's head or tail. I would say, well, it is a linear combination of head and tail. But of course, this is not quantum mechanics. It's just an analogy, okay? But the main point is that the quantum computing is so powerful because besides the basis states that it can represent, which just correspond to the classical computing, it also can represent the states, which is the superposition of the basis state. So what is such a big deal? I just show you that one qubit, right? I did not introduce qubit, but it's just a quantum bit. You see that before I say one qubit, it can have 0 and 1. It have two basis states, nothing special. Just like one bit, you can represent 0 and 1. What if I have 4 qubits? If I have 4 classical bits, I can represent 0, 0, 0, 0, all the way to 1, 1, 1, 1. I have 16 possible representation. But as I said, in quantum computer, the register is just the same as the classical register if we only operate on the basis state. So similarly, I also can have these 4 qubits to have their basis state at 0, 0, 0, 0, all the way to 1, 1, 1, 1. Note this is a basis state, the most fundamental one, right? So if I have 1 qubit, I have 2 basis states. I have 4 qubits, I have 2 to the power 4 basis states. If I have 300 qubits, I have 2 to the power 300 basis states. The same as classical computer. But remember, I can represent the information also in a superposition in all the basis states, right? So if I have n qubits, I could have a state which goes from A0 times 0 plus all the way to A0 to the 2 power 300 minus 1 of the last basis state. Okay, so what does it mean? Here I copy the equation again, but this is the main point. If I have 300 electrons, 300 qubits, it can have 2 to the power 300 basis states. And then it can represent all the information which are the superposition of this 2 to the power 300 basis states. So think about the quantum information that you have in 300 electrons. It's just equivalent to have 2 to the power 300 compressed number, because the state can be arbitrary, right? You can have it 0.2 times 0 plus something times 1 all the way. This is equivalent to the 2 to the power 90 compressed numbers. How much information is that? We only have 2 to the power 82 atoms in the universe. In the world at this time, we only have 10 to the power 21 bytes of information. If you want to represent, if you can represent a compressed number by using 1 atom or 1 byte, you see that we cannot even encode the quantum information of 300 electrons. That is another perspective. So the superposition is very powerful. It contains a lot of information. But so what? One possibility is that you can have something called quantum parallelism. Now, imagine that this side is a state of 2 qubits. It's going to be a linear superposition of 3 basis states. Now I just write it 0, 1, 2, 3, which in binary means 0, 0, 0, 1, 1, 0, and 1, 1. Now, quantum mechanics is linear. If I have able to do some operation on psi, then it will distribute to all of the bases. So basically, if I want to do a computation on this basis, you see that I can do all the computation in one shot, because first I form the superposition and then I apply the operation, right? In the so-called multi-universe or multi-world interpretation, it's just like in each universe, each world, we have one of the basis states and we apply it and it does it at the same time. So if I have 300 qubits, you can imagine I can perform 2 to the power 300 computation at the same time. That's why it's going to be very fast in this sense. So that is the first sense about quantum computing. Good. So we have a lot of information in a state. But how do we get it? Unfortunately, it's difficult. We can try to do a measurement. In quantum mechanics, if you want to do a measurement, you will cause something called wave function collapse. It's just like the spinning coin. I want to know whether it's head or tail. I push it. Then it will collapse to either head or tail, right? It only collapses to one of them. I do not know what are the alpha and beta. Similarly, if I have a state, which is a linear combination of the basis state, I do a measurement, then it will collapse to either 0 or 1. So this is an important concept in quantum mechanics. When you do measurement, it will always collapse to the basis state. And the probability, and it does it randomly, but the probability depends on the square of the magnitude of the coefficient. Okay, so you see that even I have 2 to the power 300 electron or complex number, there's no way, no strict way I can measure them directly. Okay. Now after this, then we can talk about another important concept called entangled state. Now on this slide, you see that it has a state, a general state of 2 qubits. Why I know it's 2 qubits? Because it is 0, it has 2 bits here, and it has 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1. It is a linear combination of them. The first one has coefficient 1 over 2, the second one has negative 1 over 2, and continue, right? Now, with this state, it's possible to do a tensor product, which we will not discuss in this talk, but basically, it's just like a factorization. It becomes a description of electron 1 and electron 2 separately. So this is nothing interesting because we can do it classically also. But there are some states, for example, this particular Bell state. It is also a superposition of 2 basis states, 0, 0, and 1, 1 of 2 qubits. But it doesn't have the component of 0, 1, and 1, 0, which means the coefficient in front of it is 0. You cannot factorize it to the tensor product of 2 subsystems, 2 electrons. It means you cannot describe this whole system by describing the 2 electrons separately, and they are called entangled. So they are very useful in quantum computing algorithm and quantum communication. Let's take a special case which Einstein called that it is a spooky action. If I have 2 electrons, I entangle them. In this case, I represent it as up, up, and down, down as the spin, but it's just like 0, 0, and 1, 1. You see that this is an entangled state, just like 0, 0, 1, 1. I move one of the electrons to 100 light years away, really far. But I make sure it is entangled. Theoretically, I can do that as long as I'm very careful. I don't let the noise to disturb it. Now remember that what if I try to measure this whole system? It will collapse to the basis states, right? Like the coin. So it should collapse to either up, up, and down, down. If I measure on the Earth, I can only touch my electron and then assume that it collapsed to up. But this measurement is equivalent to measurement of the whole system. So it can collapse to either up, up, and down, down, because this was the wave function we had before. And because of this, it can only collapse to up, up, because I get up. Then the electron in 100 light years away will also collapse to up. Even the person over there did not do any measurement. And that is like that I can affect another electron 100 light years away at no time. That's why Einstein called it the spooky action. But don't worry, this is not going to violate the general relativity and you cannot transmit useful information faster than the speed of light. But here, just to show you some very interesting thing, it can take days to discuss this, but I will just stop here, right? So we know quantum computing is special because every vector, every state is there, and it is so special because it operates with superposition and entanglement. But what is a quantum gate? How do we manipulate it? Quantum gate is nothing but just imagine it's rotating the state, which is just a vector in their hyperspace. This is not the space in the 3D. We cannot see it. For example, for a qubit, sometimes people make it as a broad sphere, but this is not in our 3D space. We just embed the hyperspace of a qubit. Qubit is only 2-dimensional because it only has 0 and 1 as the basis, but it has a complex coefficient. It's also not our regular 2D plane, right? So what a quantum gate does is to rotate the vector in this space to other place. And usually a gate is nothing but just a laser pulse or microwave pulse. Right? We have different gates. For example, it can be a NOT gate that rotate from 0 to 1, or from other same when you apply to other vector, you will do a NOT operation. You can have a 2-qubit gate, right? That, for example, a control NOT, which is very important, it only apply the NOT operation to the second qubit if the first qubit is 1. Now this we have classical counterparts, but there are some gates that has no classical counterparts. For example, the Hadamard gate, and it does not have because it will transform a basis state to a superposition. Here you see that if I 0, it transforms it to a superposition of 0 and 1. Of course, in your classical register, you cannot have information that is either 0 and 1, right? That is called error in classical. But now in quantum computer, you can have a superposition. So let's understand more about the gate. For a classical gate, it sometimes is irreversible. For example, a LAN gate. If you give me the output, I actually don't know what the input is because many combinations can give me 1. I cannot go back. Quantum gate must be reversible. It means that if I know the output, I should know the input. This is just because quantum gates, as I said, it is just a rotation of the vector in the hyperspace. You can rotate one direction, you should be able to rotate back, and that is just a result of quantum mechanics. So usually we see a quantum circuit, you start with a state, then you have different gates. Now this is actually the flow of time instead of the space, because in a classical computer, usually it was classical circuit, you usually see that this is LAN gates, NOR gates, adder, subtractor. You really have the circuit laying out from left to right, but that is not the case here. Usually the qubit is stationary, and as I said, the gate is what? You shine the laser pulse or microwave pulse to rotate them. So here I shine a NOT gate pulse, I shine a control NOT gate pulse, and then etc. And they are reversible, okay? The only thing that's not reversible is when you do a measurement. It will collapse to the basis state. That is about the quantum gate and circuit overview. How do we implement the qubit? In principle, I think we can use our mood. I'm 10% happy, 90% sad, for example. Of course, this is not reliable, right? We can use spin, electron spin. We heard about that. It can be spin up and spin down. And then this is the basis state. And then any state can be a linear combination of it. We can also use photonics. We shine a photon. I did not draw the path, but the one photon, it can go up and down. And then where is the photon will go? Is it up or down? We don't know before we do the measurement. So it is a linear combination of the photon on the top and the bottom path. But once we do the measurement, what happens? It will collapse. You will find that either in the top or a bottom waveguide. Mostly people use the superconducting qubit. This one is something called Josephson junction, a transmon qubit. It coupled with a capacitor form a superconducting island, but we don't need to go to detail. The point is that this island can have an excess charge of either 0 or 1 under the bias, right? So we have one extra pair of electron, or a 0 extra pair of electron, or 1 extra pair of electron. And we can have a linear combination. It means that we don't know whether we have an extra pair of electron or not. And that is how we form a so-called superconducting qubit. So you see that the most important thing is we need to be able to distinguish the energy level of the two levels, spin up, spin down, 1 pair of electron or 0 pair of electron. In that case, then we need to avoid the noise, and that is the difficulty of the quantum computer now. Because of the noise, the qubit will lose its information very fast. So on the right, I'm showing the energy scale. as a function of temperature of a thermal energy. At 300 Kelvin, our room temperature is 26 milli eV, right? Qubit separation is 0.02 milli eV. That's why we usually need to cool it to the very low temperature, like dilution refrigerator, to avoid the so-called de-coherence time. De-coherence. And there are two times. One is the T1 time that it flips from high energy to low energy level. Another is the T2 time with dephasing time. You start with a superposition of 0 and 1, and eventually you don't know what are the relationship or the relative phase of them. You lose the information again. For this overview, last thing I want to talk about is error correction, right? In a classical communication, for example, we can use repetition code. If I want to transmit 0, I make 3 0. And then if one of them fail, through majority vote, I still know it is 0. In quantum computing, there's something called no cloning theorem. You cannot copy a state, a general state. And in that case, you cannot use this type of repetition code directly. One of the most common one is the so-called syndrome measurement. It's just like I don't feel well, I go to the doctor. Did I get COVID or flu? They can either test my virus, or if the doctor is very experienced, just look at my face, my temperature, my breath, my whatever matrix. He or she can deduce maybe I just have a normal flu, right? So quantum error correction is like this. We have a qubit, we cannot measure it, because if I measure it, it will collapse, and I also cannot copy it. What I do is have some auxiliary bit, and I do some entanglement. Remember the entanglement we talked about? Basically, we just have some correlation between this qubit and the auxiliary bit. When the qubit got some error, due to the entanglement, it is going to affect the auxiliary bit. And what we are going to do is to measure the auxiliary bits, which we don't care. We are going to discard them later. And then based on the measurement, we know what happened to our qubit, whether there's a phase change or there's a flipping. Then we apply some operation to it to correct it. In this whole process, we did not do any measurement. So for the first part, this is what I want to say. We see quantum computing is very versatile, right? It can store a lot of information. But definitely you see that you are not able to get all this information in one shot, because the measurement is going to collapse everything to the basis state. So how can we get the information we want? We will do the destructive and constructive interference in the function, in the algorithm, so that we get the function, the answer we want. Okay, I won't go into the details, but I would like you to appreciate this. So as a result, quantum computer cannot replace the classical computer. It's much slower to do 1 + 1. But it will be very useful to do something the classical computer cannot answer well, like whether the function is balanced, what is the period of the function. This is related to encryption and the optimization problem. So in the future, I expect quantum computer will be a very powerful accelerator for the classical